Okay. So first, thank you for having me talk. I'm here to discuss microsimulation modeling. This work is combined work with Abdullah and Jyoti. They are two doctoral students I work with at UIC, as well as with Wael and Rob, who are at Dark Peak, who I'm sure you all know quite well. All right, so why you should think about doing microsimulation. In case you aren't a person that does them, they're really helpful when you want to look at things that get complicated, when individual variability matters. So we all know the Markovian assumptions. I have them tattooed on my forearm, actually, of our memoryless properties. We're using population averages, and oftentimes you'll get into situations clinically where that just doesn't work anymore. One of those, which we'll talk about, would be diabetes. So diabetes impacts all sorts of different aspects of the body. So microvascular and macrovascular complications. There's a host of events that then impact each other. So very quickly, you're going to have a state explosion. Um, However, you might say, okay, I know that microstimulation models are out there, and if I need to do one, smarter people than you, Aaron, have written packages that I can use. And that's true. So for many situations, you can use these off-the-shelf packages. Um, However, more often than not, when you're building a microsimulation, it's pretty complicated. There's always little weird, wonky parts of it, and they're usually going to require customization or something a little more. Additionally, why I did this study at least is for myself 19 years ago when I was 21. This is when I started doing microsimulation models, looking at this diabetes model, and we were using Excel. And it was slow. I remember the physician I was working for, he had a big deadline, and I remember he would have to come to campus in the middle of the night to restart a simulation and harvest results. There wasn't a lot of guidance out there. That said, things have changed. We have some great tutorials that have been published. And so this is really building off that work. Additionally, this is really, you could view this as my like independent study from a class I took from Robin and his group at Dark Peak on creating microsimulation models. So the objective of this talk is really to prove that microsimulations aren't very hard in R. Vectorization is a fancy word for something that's very simple and easy to do. And using C++ with RCPP isn't that hard. It's still a little hard though. So the case study that we're going to be building a microsimulation model with will be based on the United Kingdom prospective diabetes model. So the UKPDS model. This is a model that's been around. I've been using it for almost 20 years now. They've updated it over that time period. But briefly, it's a well-known diabetes simulation model based on over 5,000 patients enrolled in the 70s and 80s. It's been following people up continuously for 30 years. And this is what the model really looks like. So if you're trying to understand this model when we later are writing code or looking at a spreadsheet. So you have a patient and they have biomarkers, meaning like their blood pressure, their A1C. These then feed into a series of risk equations, which are really just parametric survival models, mostly Weibull models, that predict if a person had an event in that period. Then, based on events and biomarkers and patient characteristics, this influences if a person dies or not. This is actually 4 different equations that do this based on a person's history. And then a patient cycles through. Again, we update their biomarkers using OLS type equations, and we run through the whole process again. Once a patient dies, you select a new patient. And so this is what microsimulation is, and this is how we do it within diabetes. And so how do you actually build a microsimulation model? So this kind of talked about it broadly, and this talks about it specifically. And so we create a patient, we create a coefficient matrix. So we take all the equations that the nice folks from Philip Clark and his colleagues published about these risk equations and biomarker trajectories. And we take those coefficients, we turn them into equations, and then we simulate patients, we store their output. Okay, so let me show you what this looks like in Excel. And yes, it does feel like you're using a typewriter at that point. All right. So here is a simple microsimulation model. We have a few tabs here. So here we have our population. So I have 250,000 patients that we're going to want to simulate through. For each patient, this is set up like a normal data frame or data set. We have all of their patient characteristics at baseline. So this is our population that we're going to start with. We have a little macro that's run that takes a patient's line of data and then pastes it up here. You can see this has already run previously, and we have the last patient still there. Then we have a coefficient matrix. So what do I mean by that? If you aren't used to doing this, you might say, you're saying a bunch of words that don't make a lot of sense to me. So here, this was a OLS-like regression equation. Here are the beta coefficients listed here. This is what that beta coefficient is for. So this is duration of the log time of duration of diabetes. And this is how it influences HbA1c. And so we created a matrix for all of the equations that we'll use. And so for each column is a different equation, a different thing that we're trying to predict. So here it's LDL. And then these are all the potential parameters that could be used. Here, the lambda is really the constant for many of these models. And so you can see we have many equations that we'll be pulling from, but they're all stored here. Then we move to our next tab, which is our model tab. So this is our patient trace, if you will. So patients enter the model and they pull from data up here in this line. And it's populated based on each individual. And we, again, have this loop that will run as a macro. And this populates this spreadsheet. And then we have patient characteristics, some which change over time, such as age, some which don't, such as the age a person was diagnosed. And then we have many things that we're predicting. So looking, for example, at a biomarker here, we have a simple equation, which is just matrix multiplication. We have set up the data, or we have set up our patient trace columns so they're identical to the columns here in our parameters. This allows that we can do matrix multiplication without any problem. And then we just add the constant. So this is what we're doing for our biomarkers to predict them over time. There's lots of different transformations and lags and things that this model requires for these biomarkers and how they're used later. And then we have things like our events. So congestive heart failure is one of the events that we're interested in. And so here again, you'll see we're just using matrix multiplication to multiply your patient characteristics times your beta coefficients to get your quote unquote linear predictor. You have to do, you use this, you do a couple transformations to get it to be your cumulative hazard at that time point. Then you subtract it from the next time point to get your transition probability. There's a little bit more math, but generally that's what you're doing. And so that's how we create this micro simulation model. And so we have a lot of patients, we have a lot of coefficients, but actually it's not that hard to do once we start utilizing matrix multiplication. And then we have our summary column, or our summary tab here. This is where we're collecting data. Right now, I'm just collecting total life years, but this is generally how this model is built. And so you're probably asking me, Aaron, why are we talking about Excel here? I think it's worth going through that because that is where many people know how to model. And I think that makes transparent what we're going to do next in code. So it took 103 minutes to run 250,000 people through that Excel model. So now let me show you how you do it in R. And so the first thing is we're going to do this as a really just like that model, one person at a time. So first you have your coefficient array or matrix, and here this just shows you the code on how to do that and name your columns the right way. And this right here is, once you do all that, how you can create your matrix or array. Of note, we break it up into two pieces, the parts that change over time for individuals, and essentially the constants and the row parameters for time to event models that we don't need to update. So that just makes it a little bit more efficient to run. So we create this coefficient matrix that we can then use, as you saw earlier, to do matrix multiplication. And so now with R, how do we get the patients into the data? Again, we have a data set that we just load. Then we create a patient trace that will have the right dimensions. And we now have to have code that pulls one person at a time, does any sort of manipulation. So there are some variables that need to be divided by 10 or multiplied by 10, standardized in some way. But so we have to have this function that pulls a patient out at a time, gets its data ready, and then populates that first row of the patient trace. So this is, really similar to what we just walked through in Excel. Okay, so now we have the equations we need to think about. So before in Excel, we had them within those cells where we were just doing matrix multiplication when we were looking at predicting a biomarker. It's the same thing in R. It's a very nice parsimonious piece of code where we have patients' individual traits from the prior period. That's all that this is doing. And we do matrix multiplication, so that's what this symbol means for the biomarker event of interest. And that we change up here with when we have the function. So that's all you do to predict a biomarker. And this is a little chunk of code that we'll be able to use across all of our biomarkers, across all of our cycles. So it's quite quick to run as well. Here for a Weibull model, again, this is very similar to what we saw before. Here we have our patient factor. So this is, again, just matrix multiplication. And then we compute the cumulative hazard at t plus 1, and then you have your transition probability. One of the things I love about R, or a scripting language compared to Excel, is how easy to see what's going on here. This isn't buried in a cell that you have to kind of take apart. It can be so clear and concise and easy for the next user to use. And again, this is a piece of code that we'll be able to recycle each cycle for each patient for many different events, for really all of our events. Okay, and so when you do this, the runtime is about 10 minutes. So we've obviously improved quite a bit, but we think it could be even better. However, we're all quite happy that it is in 107 minutes or whatever that was. So now we need to think about vectorization. And this is a word, when I've read it before, this has always kind of scared me. So this is an artist rendition of me when thinking about arrays. And so what is an array? So when I first heard about these and they're described, it was actually Rob that was describing them, said, instead of thinking about time as a data set and you're going down, think of it as you're moving through time. And each slice, if you will, is a point of time. And so as an American, I thought of American cheese, Kraft singles, and that you have this cube, and that each moment in time, we're progressing through this cube. So that's the big change when we're thinking about vectorizing this model, is we actually change the data structure. However, it results in code that's almost identical. Okay, so first, how do you set up the patient trace? So as I said before, we have to move time from going down to time going into into a third dimension. What changes is, instead of one individual at a time, we have everyone lined up here. And now when time goes, everyone is just taking a step further in that time. Okay, and so the code to do this is so simple and easy to do, is to create this new array. Here's a side-by-side comparison, and you can see instead of n row and column, it's slightly different syntax where you say what the dimensions are and the dimension names. These are all referencing lists or previously created variables, so it's very, very easy. And then how do we update some of these functions? They're actually very, very similar. If you look, they're almost identical. So the big difference is this right here. So before we were saying we're going to give you the whole patient trace and we're going to tell you which time point. Now, actually, we just give a matrix. So we give one slice of that patient array and we say we don't even have to index within there. So up here, when we're talking about the function, we'll say, just look at this specific slice. And that's all that changes in our functions that we'll use over and over again. And so when we did this, yeah, the time decreased dramatically. And I think it's worth pointing out that when I did it, it took 55 seconds. But when Abdullah and Wael did it, they were able to do it quite a bit faster than I did. So there's still some finesse elements that go on here that I have yet to achieve myself. Okay, so then we're getting to the next point, and I'm running out of time, I see, where we're thinking about how do we make the code go even faster? And this is where parsimonious use of C++ can really help. And to do this, don't rewrite all of your code. Use profviz, a package that will help you identify the parts that are taking a lot of time, and you just focus on those parts. You pull them out, and then you can do individual runtimes to compare how fast things go. So we're going to use our CPP here. And so here I'm showing you another function to predict an event. So this is a Gompertz model. And to show here how different R code is and C++. And the big difference is it is so picky. C++ is so detail oriented. You cannot assume anything about it. And so there'll be, you have to predefine everything. However, you only have to do this pain and suffering for small amounts of your code. Again, you update for me, the biomarker function. You update a function about Weibull models and Gompertz models, but everything else can stay in R. So you can use our C++ to further make your model go even faster. Additionally, you can use parallel computing for your probabilistic sensitivity analysis to scale this and make it go, again, even faster. Definitely couldn't do this with my Excel model. Okay, so the key findings of this would first be Excel is slow for microsimulation models. They can work. You can make them work, but they're often quite slow. Whereas microsimulation models, especially ones that are based on regression oriented or based on regressions, can be written in a really parsimonious, easy to write way using just R. Moreover, going from a one person at a time model to a vectorized, or you're running like an entire cohort of individuals, still as individuals though, at the same time, requires very small coding modifications. Really, it just requires you to think in 3 dimensions instead of 2. And moreover, you can increase speed with minimal use of C++ by just optimizing specific functions that might be taking a long time. All right, so I think I still have time for questions.
Well, we're slightly over. There's one question in the chat.
Okay.
If you want to address that, it's from Howard.
Sure. Does the array trick work if event times are history dependent? If a rate stroke? Absolutely. This is the exact reason why I needed to learn how to do this, and I went to Rob's workshop, is because in diabetes and all sorts of diseases that I work in, history is incredibly influential in the risk of an event today. Moreover, biomarkers in a diabetes model change every period, and you need to have those updated biomarkers change the risk of events. And so, yes, these models, if you have this array approach, yes, it should explicitly be able to handle these sort of potential issues.
Awesome. Okay.